Alright, in this video we're going to introduce a new topic, standard enthalpies of formation, and we're going to see how we can couple that with Hess's law to calculate enthalpies of reaction. Alright, so I've talked about standard state enthalpies before. Just as a quick reminder, when we have standard state enthalpies, that means a number of things to us. If we have a standard state enthalpy, that means all gases are at a pressure of 1 atmosphere. If we have substances in solution, it means their concentration is 1 molar. And for solids and liquids, the standard state is the pure liquid or solid at 1 atmosphere. To designate that we have a standard state enthalpy, we put 0 as a superscript to the H, and we pronounce it naught. So standard state enthalpy, I would talk about this as being a delta H naught. And while standard state enthalpies imply 1 atmospheric pressure, they really can be any temperature. Very often, the enthalpies are given at 25 degrees Celsius, but they don't have to be. So we just want to be aware of what temperature these standard state enthalpies are for. Alright, so we can have any enthalpy in its standard states. But now I want to talk about a very specific enthalpy. And so for any compound, we can talk about what's called the standard enthalpy of formation. And we represent that as a delta H with a subscript F, right? F being for formation. And this is a standard state enthalpy of formation, so we also include the naught. So this is the enthalpy for a reaction to form exactly 1 mole of that pure substance from its constituent free elements in their most standard states under standard conditions. Right, so that's a mouthful. So let's look at an example of a standard enthalpy of formation. In this case, it is for gaseous carbon monoxide. And so in the enthalpy of formation, I'm making 1 mole of the compound that I'm interested in this case carbon monoxide, and then the reactants are going to be the elements that make up carbon monoxide. And they're going to be in their most stable forms under standard conditions. And they don't tell us the temperature, so we'll assume that it's 298. And so right at room temperature, 25 degrees Celsius is roughly 298, carbon is going to be solid and oxygen is going to be a gas. And of course, oxygen is one of the elements that exists as a diatomic molecule, so the most standard form of elemental oxygen is O2. So I need 1 carbon, so it's just carbon solid, but for the oxygen, in order for it to be balanced, because I have to use O2, but I only want 1 oxygen in the products, I have to use a fraction. So I have to use 1/2 O2, because in the standard enthalpy of formation, I have to form 1 mole of the product. So I can't change the numbers of carbon monoxides. I had to adjust the oxygen. So that's why we end up with a fraction there. So let's do another example. Let's say we wanted to write the chemical equation corresponding to the enthalpy of formation of methanol. And I should have told you I want liquid methanol. So my product is going to be 1 mole of methanol. And so the elements I need, carbon would just be C solid. Right, I need 4 hydrogens. And hydrogen is H2, so I'm going to do 2 H2 gas, and then I want just 1 oxygen. And as we said before, oxygen is also O2, so I'm going to have to use a fraction again, and so I'll have 1/2 O2 gas. So that would be the equation corresponding to the enthalpy of formation of methanol. And now an important thing about enthalpies of formation of an element, those are defined to be 0. You can kind of see why that would be, right? The enthalpy of formation of, say, carbon, right, would be making it from its elements in their standard states, right? And so nothing's happening there, right? That is no reaction, or that is not a reaction. And so the enthalpy of formation of any element in its standard state is defined to be 0. Okay, so this may seem like sort of an abstract, weird thing to define, but it's very useful to us, as we'll talk about on the next slide. So we can combine enthalpies of formation and Hess's law, and then for any compounds that I know their enthalpy of formation, I can calculate the enthalpy of the overall reaction. So if I have a chemical reaction and I know all the enthalpies of formation of the compounds that are involved, I can always calculate the enthalpy of that reaction. And so this can allow us to calculate the enthalpies for lots of different reactions. And then rather than sort of recording the enthalpies for different reactions in tables, I can just record the enthalpies of formation of the different compounds. And so that greatly reduces the amount of information that I have to store. And so the way we do that, to calculate the enthalpy of a reaction, I can just add up the enthalpies of formation of the products and then subtract from that the enthalpies of formation of the reactants. And I can see that there's an error in my equation here. What these C's are in front of all of these shouldn't all be C's. These are the molar coefficients from the balanced reaction. So if I have, 5 moles of C, then C would be a 5. So these should be specific to, right, that should be a D and an A and a B. All right, now this may still be a little bit abstract, and so let's look at an example. Right, so let's say I wanted to calculate the enthalpy of reaction for this compound using the enthalpies of formation. And so what I would do is I would go to a table that has all of these enthalpies of formation. If you look at the back of your textbook, you can see the enthalpies of formation of a lot of compounds are listed there. And if you do that, you'll see a table that looks kind of like this. And so for different elements, it'll list a bunch of compounds. So here we have aluminum and iron. And then in the table, here are the enthalpies of formation. And then you'll also typically see these. And we're not going to use these this semester, but we will next semester. And so this is a free energy of formation and a standard molar entropy. So we don't have to worry about these for now. We're interested in the delta H's. And so all we have to do is take our chemical reaction and look up the enthalpies from the table. And so we talked about the fact that an element in its standard state, its enthalpy formation is going to be 0. And so you can see that represented here for the aluminum and the iron. And so on tests and quizzes, if we had an element in its standard state as one of our reactants or products, I might not give you the enthalpy of formation, and I would expect you to know that it is 0. So the enthalpies of formation, we need aluminum, we need aluminum oxide, we need iron, and we need iron 3 oxide. And so we need to be sure we get the right one. I don't want Fe3O4, I want Fe2O3, so I would use that one there. So let's go back to the previous slide. Right, and now we have the enthalpies of formation that I need. Right, and I didn't put the enthalpies of formation for aluminum and iron because I know those are 0, and you should know that those are 0. And so what we need to do is add up the enthalpies of formation of the products and subtract from that the enthalpies of formation of the reactants. So it's always products minus the reactants. And so the delta H naught of this reaction, because these are standard state enthalpies of formation, so the delta H that I calculate will be a standard state enthalpy. Right, I have 1 mole of aluminum oxide, and so I'd have 1 times negative 1676. I have 2 irons, and so I'll write it in here even though we know it's 0. 2 times 0. And then the way we write this can be different. What I usually do is subtract and then do all the reactants together. And so I have 2 aluminums, so it's 2 times 0. And then my other reactant is iron 3 oxide. And I have 1 mole of that times negative 826. And so you could punch all this into your calculator, but the only tricky thing here could be the signs. And so let's be a little bit careful. So the products come out to be negative 1676. And then for the reactants, right, this is going to be 0. And then I'm going to have negative 826, but I'm subtracting that. So when I subtract a negative, it's going to be positive 826. And so then when I add those numbers together, I get negative 850. But because I know the ones place in both of these numbers, that 0 is significant. And so if I put a decimal place there, then I'm telling everybody that that 0 is in fact significant. And the units are going to be in kilojoules per mole. All right, here's another example. So same type of thing. I want to calculate the enthalpy of this reaction using tabulated enthalpies of formation. And so we would go to the table. All right, so here is the table. And then we would find all of our compounds in the table. And so I have the SiCl4. I picked this example specifically to point out that phases are important, right? So in my balanced chemical equation, I have liquid water, and there are two entries for water in this table, one for liquid and one for gas phase water. So I want to be sure that I use the right phase. So in this problem, I'm interested in the liquid water, and then we've got the silicon dioxide and the gaseous hydrochloric acid. All right, so here's some more space for us to work. And so I've collected the enthalpies that we're interested in. And so again, I'll do products minus reactants. So I'll do the SiO2. So that's going to be 1 mole of that times negative 911. And I have 4 moles of HCl. So it'll be 4 times negative 92. And then I subtract the reactants. So I put all the reactants in brackets. And I have 1 mole of silicon tetrachloride. So negative 6, well, to be consistent, I'll put in the 1, right? So I've got 1 times negative 687, and then I have 2 moles of water. And again, at this point, you could punch all of this into your calculator at once, but I'm going to break it up into 2 steps just so we can see what's happening with the signs a little bit better. So negative 911 plus 4 times negative 92 gets me negative 1279 for the products. And then minus, for the reactants, I have negative 687 plus 2 times negative 286. So that's going to be minus 1259. And then again I have, right, that's a 9. And then again I have, I'm subtracting a negative, so that's going to be a positive. So negative 1279 plus 1259. And so that leaves me with a delta H naught of reaction of negative 20. But again, that 0 is significant, so if I put a decimal point, I'd be letting everybody know that. And then we have the units again are kilojoules per mole. All right, and again, if you want to see any more examples of these, I've got another video with an additional example.